Darlene Christ. I'm the Community Engagement Manager for the Ocean Observatories Initiative, and we're really delighted and grateful to have the lightning talk presenters who presented earlier this week do it again for us. So thank you. But now I turn it over to Ed Deaver, who is the PI of the Coastal Endurance Array, and he's at Oregon State University, and he will moderate this session. To you, Ed.
Well, thanks a lot, Darlene. Yeah, thanks all for joining us, and thank you for the lightning talk speakers for agreeing to present their talks again, in addition to the posters and other things they've done here at AGU. We've got 5 presenters here today, and the format is going to be each lightning talk speaker is going to present their one slide of their poster, and then we're going to follow that up immediately with a chance for some discussion and questions, and then we'll be moving on to the next speaker. So without any further ado, our first speaker is Bill Chadwick from Oregon State University, and he's going to be talking about OOI monitoring at Axial Ridge since its 2015 eruption. Thank you, Bill.
Okay, so let's see, share my screen here. Yeah, so these talks were meant to be just 1-minute quick little summaries of, you know, to entice you to follow up with, you know, seek more information. So this is basically a preview of the poster I'm presenting at AGU this afternoon, actually, in person, and there's also an online version. So I invite you to check that out if you're interested. So yes, this is looking at OOI data since the 2015 eruption at axial seamount, and specifically looking at the pressure data that we use to monitor the vertical motion of the center of the caldera, and also seismicity, which William Wilcock is the main person who looks at that. So this is a collaborative project. And so this plot is looking at the number of earthquakes per day starting at the beginning of 2015 till you know, till now. And the number of earthquakes are shown by the black histogram. So there were thousands of earthquakes per day here leading up to the 2015 eruption. Then right after the eruption, it dropped down to only about 10 per day for several years. And then in about the beginning of 2018, we started to get up to a few hundred a day, perhaps, but it's been quite variable. So also on this plot in the blue is the inflation deflation signal we have from the pressure data. So here it was inflating up to the beginning of the 2015 eruption. It deflated 2.5 meters and then was reinflated very quickly, but the rate has decreased about by an order of magnitude since then, the rate of inflation. So there seems like on first glance, there's 2 different things going on. Inflation was fast and now it's slow, but conversely, the number of earthquakes were low and now they're higher. So how are those 2 things related? And the poster, my poster is about, we found that actually the cumulative number of earthquakes has been rising exponentially with the total uplift since the 2015 eruption. So the more uplift we have, the greater the number of earthquakes. And this is a relationship that's predicted by a model that Kilburn has been publishing about. And these are just 2 ways of seeing the same thing. This is cumulative number of earthquakes. This is number of earthquakes per meter of uplift. So anyway, if you want to hear more about that, you can ask me a question now or come to the poster or email me or whatever you want. That's all for me. Thanks. Can't hear you, Ed.
There, I am now unmuted. So thanks very much, Bill. And yeah, please do show up to Bill's poster if you're registered for AGU. But if you're not registered for AGU, maybe this is a great time to ask a question. And I'll leave it to the attendees. I think Darlene, you'll unmute people as they raise their hand or otherwise make their kind of intention to speak known.
I'm happy to do that. So if anybody has a question, please do raise your hand. In the meantime, I do. Bill,
Okay.
all the seismometers on axial seamount, do you think they're adequate to be able to forecast, excuse me, I know we're not supposed to use the word predict, but continue to monitor and forecast what's going to happen?
There's 7 seismometers in and around the caldera. So I guess that's enough to, have to detect the earthquakes in the caldera, but it's definitely not enough to see what's happening on the rift zone. So axial has a summit caldera, and when it erupts, dikes usually intrude either north, it can be tens of kilometers or south. And so once the magma leaves the summit, the existing network of seismometers can't really follow the propagation of magma away from the summit. So it's kind of yes and no. It can tell us what's happening at the summit, but not the rift zones. But William Wilcock has gotten a grant funded to deploy some ocean bottom seismometers that won't be connected to the cable. That'll be autonomous for a couple of years. But the tricky thing with that is, knowing when to put them out, and then you can only keep them out for so long, and hopefully something interesting is going to happen while they're out there. The luxury of having the OOI is that it's monitoring all the time, and we don't have to worry about recovering instruments, and we're going to be monitoring when whatever happens next happens. So it's yeah.
Thank you. It's complicated business down there.
Yeah.
I have a question. If there's no more questions, I don't see any from the attendees right now, but
Sure.
a pretty naive question. With the earthquake activity down off of Cape Blanco last week, is any of that related, or does that have predictive value, or is the work that you're doing totally focused on what's happening there on caldera and the signals that are present there?
Right. The earthquake swarm last week was on the Blanco fracture zone. So that's a strike slip fault that meets up with the southern end of the Juan de Fuca Ridge, which is spreading, and axial's on the Juan de Fuca Ridge. So it's a different tectonic environment, and it's far enough away that it probably didn't have any effect on axial. I mean, we actually could see the ground shaking on the OOI instruments. It was close enough to see the earthquakes, but I didn't notice any changes in what we monitor. So it was, interesting, but not didn't seem to affect axial in any way that I noticed anyway.
Thank you. And we have a question coming in now from Martin Sherwath.
Okay.
Hello. Yes, thanks for unmuting me. I was just intrigued by the periods when there was a little bit of subsidence and accompanied apparently by little seismicity. And I was wondering if there are several bottom pressure recorders that all were sinking, or was the data of just one? So how widespread is the monitoring for the whole volcano?
Yes, very, very astute observation. Let's see, I can jump back to my slide here. Yes, you're talking about these little notches.
Yes.
We call these short-term deflation events. And yeah, there were 8 of them that between mid 2016 and 2020. And yeah, you're right. During each of them, the level of seismicity dropped. It's more apparent after the level gets elevated, like here. And this one was particularly noticeable. And there's also one in here. So, this record is actually this blue curve is actually a differential curve. So the difference between two bottom pressure recorders. So it's the difference between this one at the center that inflates the most versus this one on the eastern rim that inflates the least. And we do that because by differencing, it takes out a lot of the oceanographic noise that's inherent in the pressure data. Anyways, it helps us see things like this more clearly. But yes, at the time, for example, at the time of this short-term deflation in June 2018, we have 9 bottom pressure recorders throughout the caldera. From the northernmost one was up here, the southernmost one was way down here, and they all saw the event. And that is described in a paper that this work and looking in more detail at these short-term events is described in more detail in a paper that's almost in press in G-Cubed, and a link to a preprint of that paper is on the poster, either in person or online. So you can, if you want to hear more about that, you can look there or email me and I can send you a link.
Sounds great. Thank you.
Good eye. Thanks very much. Yeah, thanks very much, Bill. And yeah, with that, I guess if there's any more questions, please do visit Bill's poster or feel free to contact him, I guess. And we'll be moving on to our next speaker now, Liz Ferguson of Ocean Science Analytics. She's going to be presenting on her poster, Coastal and Offshore Oregon Marine Mammal Ecological Study. Thank you, Liz.
There we go. Hopefully you guys can hear me now. All right, so thanks. I totally need to shorten the name of that as well, because I don't know what I was thinking. It's very long, but thanks everyone. I'm Liz Ferguson from Ocean Science Analytics. And as you mentioned, the information I'm presenting here is regarding the Coastal and Offshore Oregon Marine Mammal Ecological Study. And we utilize passive acoustic data predominantly from the several of the hydrophones along the coastal endurance, as well as the cabled marginal array, both along the shelf and on the slope and at the base slope. And essentially what we're kind of presenting at the conference today is more about how or describing and kind of characterizing the habitat use, or the habitat that is being used by these marine mammal species. And we found through the acoustic data that there's quite a bit of biodiversity within the region. This particular data in the figure here is a month worth of data from April 2018. And so I know realize it's a little bit challenging to see there. It's a little bit easier in the poster when you zoom it out. But I have a bit of percentage occurrence for delphinids, fin whales, humpbacks, and sperm whales that all occurred during that month of April on the slope. And what we did for this particular part of the effort for this poster for AGU is we started to kind of mix in some of the physical oceanographic data, both from the in situ instrumentation at that particular site on the slope, and also through the integration of remotely sensed data, some ocean color data. So the poster, which you have a little number there for, shows some of the remotely sensed data for with respect to CDOM and chlorophyll, as well as phytoplankton carbon biomass and net primary productivity. I think two other parameters, sea surface temperature and mixed layer depth. So we're trying to get an idea of what the habitat is like during these months when there's in association with these marine mammals. And ultimately, we're interested in looking at long-term shifts in that biodiversity of marine mammal species, as well as any changes in the habitat use. And as part of the related effort, so we're slowly trudging through the historical data from 2017 and 2018. And as part of that, as we move along, we find all these great projects to kind of tack on. It's slowing us down, but we'll get there eventually. But two of our related efforts include evaluating soundscape metrics, or sorry, the influence of marine mammal call parameters on a suite of soundscape metrics. And we're taking a look at those suite of acoustic indices and correlating them to things like call amplitude and peak frequencies and things along those lines to see if there's any relationship there, because it's a rather new introduction into acoustics and it hasn't really been evaluated for what is influencing those indices. And then as a secondary little project, we're collaborating with the University of St. Andrews to study the occurrence of burst pulses from the delphiniid events, acoustic events that we've encountered predominantly at the 106 at the shallow site. The species, well, we can't actually determine what the species is for the delphinids because there's a lot of overlap in the signals, but they do tend to have this, delphinid species at these sites tend to have this very frequently burst pulsing sound that they emit. So we're looking at the pattern sequences of those burst pulses, seeing if there's any information we can gain out of that. So yeah, it's a little bit about what we've been up to.
All right, thanks very much, Liz. And if I understand the code on your poster, you actually presented your poster back on Tuesday, so there won't be an opportunity, is my understanding, to see the poster. So this is a great opportunity to ask questions, and also I'm sure you're happy to entertain follow-up questions from folks after the meeting. Okay.
Yeah, definitely.
Great.
And I was going to put in a little chat, like you can set up a chat thing on your iPoster. So I was going to set one of those up for tomorrow as well. So.
Oh, is your poster tomorrow? I'm sorry.
Oh, no, you're right. It was
Tuesday.
Tuesday. It's just, I think you can set up a chat for any time,
Okay.
like when you're there for any time.
Great. Looks.
Got your hand up.
I have a very naive question. Thank you. It's so interesting to me. But how many hours? I understand the hydrophone data goes on all the time. So how many hours does it take to come up with an analysis like this?
Now that we have some established methods for kind of extracting the data and some processing methods, it takes, I would say, approximately maybe a week to get through 4 to 5 days in order to get through a month's worth of data. So that's kind of, now that we've got everything kind of managed and we know what we're looking for in terms of the noise and what we can kind of disregard, because it's not a fully automated process for evaluating the data or processing it. We run through and use a suite of machine learning algorithms as part of PAMGuard in order to detect what's there, multiple species that are there using their inbuilt detectors. But then we have to have an expert bioacoustician go through and kind of weed out all of the noise and parse out those acoustic events. So we're just selecting we call the true positives or the actual calls. We're trying to refine that a bit, and we're working on some deep neural network methods to be able to streamline that, but it's a big learning curve for me. So take a little bit before we get there.
Thank you.
And it looks like John Trowbridge, I think, has a question.
Yeah, thanks, Ed. Nice talk, Liz. And you answered part of my question when you answered Darlene about the algorithms that you use. It seems like you have an array of sorts because there are multiple hydrophones. Is there anything you can do about direction or range?
Oh man, you know what? I'm actually involved in a little bit of that. I'm working with some time-aligned sparse array data right now in PAMGuard, and I can truly attest to the fact that it would be possible if there was a time-aligned element to these, and they were time synchronized. So the biggest issue ends up with the fact that you can't confirm that they're time aligned, and there's naturally drift that occurs within all of these instruments. So using time difference of arrival methods of determining a bearing or even location, or sometimes even a location to an animal, becomes pretty impossible without that element. Now, if you had a pinger out there, yet another instrument to throw on there, and you had a means of being able to kind of correct for that, then potentially it could be used in that way. Now, there's also some, I don't know enough about it, but I do know that Aaron Thode at Scripps Institution of Oceanography has started to work with the lower frequency data of some recorders and using azimuth in order to work out an actual direction. And I guess it can determine if there are individuals potentially calling, but that's not something that can be done with these particular recorders, and you need that other data. And I'm not familiar enough with it to know how exactly you can process the data in that way. But I think it would have to be from those other, oh gosh, the earthquake files, the ones that I don't deal with because I like the broadband stuff.
How good does the timing have to be?
Well, maybe, John, you can take that question up with Liz offline here in a minute. We're going to stick in the world of ocean acoustics for the next talk, which is from Artash Nath, and it's using cabled array data from ONC, but even more awesome and compelling is he's doing this while a 10th grade student in Toronto, Canada. So go ahead and take it away, Artash.
Thank you. There you go. Hi, everyone. I'm Artash, a grade 10 student from Toronto, Canada. And it's great to be back at the AGU. In fact, last year, I presented on the seismic silences of Canadian cities during the COVID-19 pandemic. And this year, I've extended my projects to global oceans to understand whether there's been a decrease in ambient noise in the oceans caused by humans during this pandemic. So I aggregated hydrophone data from the Atlantic, Pacific, Arctic, and Mediterranean. Now, anthropogenic noise in oceans caused by shipping traffic usually happens between 20 to 500 hertz. So I downsampled my data to 2 kilohertz. Then I calculated the power spectral densities for my data set. I calculated the geometric means and the quartiles for my data set in the 1/3 octave band centered at 63 hertz. Now, my results were in fact very interesting. So on the right are the results for the Pacific Ocean from MBARI and Ocean Affairs Canada. And it shows for each month over the years from 2018 to 2021, what was the level of underwater sound caused by humans. And it is very clear that in 2020, which is shown by the blue box, there's a very rapid drop in sound levels. And in fact, this drop is between 1 to 2 decibels in the early months of 2020, in which the pandemic was most stringent. And this result is similar for both Monterey Bay by MBARI, as well as more on the northern side in the Georgia Strait of Canada. So to avoid and reduce the effects of wind speed and other weather-related data on my analysis, I will be comparing days with a similar level on the Beaufort scale. So more analysis coming in the next few months. However, as you can see from the map on the left, I have not managed to find any hydrophones in the Southern Hemisphere yet that record from 2019 to 2021. So if anyone knows of such hydrophones, I'd love to hear about it and include it in my project. Thank you very much.
All right, thank you very much, Artash. And we'll go ahead and take questions now. And I'm itching to ask a question if nobody else is there. So my question is, oh wait, no, we've got an attendee. Looks like Abigail Ernst Beck, you've got a question here.
Hi, can you hear me? I was just wondering how you picked the 63 hertz and what specific types of noise you would get in those first and third octaves centered around 63 hertz.
Yeah, great question. So 63 hertz is around the frequency in which the noises caused by shipping traffic is highest and most dominates that band, whereas noise caused by other natural issues is much lower and less dominant in that band. So I do plan on looking and checking for which other bands my analysis works on, specifically the 125 hertz band with a 1/3 octave, as well as the 2000 hertz band, to see if my results hold true, as well as with the comparisons of the Beaufort scale, as I mentioned in the presentation.
Thanks.
Any other questions from the attendees? Well, okay, I guess I'll get to ask my question now. What I find pretty remarkable about these two locations is Monterey Bay actually 2021 rebounds maybe even more, above the pre-pandemic level of noise, whereas Georgia Strait is still relatively quiet in 2021. Do you have any initial thoughts on why that might be? I know it's probably a pretty weird explanation if there is one.
That's a great question. In fact, I do have some theories about why this happened. So in the Monterey Bay, which is near the port of Vancouver, which means that these noises are most affected by global shipping traffic, right? So it would have decreased in the early months of 2020. But in 2021, shipping traffic has mostly rebounded into global shipping. So it has gone back up to even higher than pre-pandemic levels. But on the other hand, in the Georgia Strait is much more serviced by ferry services and less by shipping traffic and more by local shipping transport. And while global shipping may have gone back up in 2021, a lot of lockdown restrictions related to transport within the country and luxury for ferries would not have been gone back up, which is probably why it has stayed down in the Georgia Strait.
All right. Yeah, fair enough. Thank you. And Darlene, it looks like, wait, let me just check the attendees as well. Okay. Looks like Martin has a question. Martin Sharwath again from the attendees group.
Yeah, I just wanted to follow up on that point of that great question, why the shipping noise hasn't recovered in Georgia Strait. And I think another factor there is the lack of these cruise ships as well. So there's a lot of, or there used to be a lot of cruise ships coming down, and that wasn't happening since the pandemic. So that could be another factor. It probably depends exactly where that hydrophone was located, because the Port of Vancouver itself probably has some more traffic now, but maybe not as much. But if that hydrophone was slightly off the port or a little bit further away, then that's definitely would have been the cruise ships that are gone now.
Yeah, for sure. Yeah, the Monterey Bay hydrophone is more off the coast and a bit southern compared to the Georgia Strait hydrophone, which was probably much more serviced by cruise ships and local transport.
Okay, thanks very much. I see you've got your hand up, Darlene. I don't know, did you want to ask your question now? Or?
If it's okay, Artash, I just wanted to know what prompted your interest in the sound in the ocean. Given that you're in 10th grade, I just wanted to hear a bit about your personal experience.
Sure. Well, the main theme of dealing with and understanding the differences in noise, both on ocean and in land, during the COVID-19 pandemic started in the summer of last year, when all schools went under lockdown and I had a lot more free time. So that's when I started my project on seismic data, right? So that was dealing with the changes on surface level changes, right, caused by the decrease in traffic during cities, right? So after that project, it turned out very well, and I was able to get very great results. I was able to measure reductions of almost up to 50% in many Canadian cities during the lockdown. And a lot of the methodology and learnings I had from the seismic project were in fact applied in this project, specifically the frequency analysis and power spectral densities. So I think working with real data and especially linking real data to a real world problem like COVID-19 and pandemics, something that really interests me, which is why I decided to pursue these projects.
Very cool. Thanks so much. And I just wanted to ask, have you presented your poster already, or is there another opportunity to chat with you, as Liz indicated, before the end of the meeting? Or
you can reach out to me on Twitter or my email, which is at the bottom of the slide. I gave the first lightning talk earlier. This is not a poster this time.
Okay, great. Okay, thanks so much. Our next talk is a pre-recorded talk from Leslie Smith of Your Ocean Consulting. And this presentation was prepared and it's narrated by Leslie, who's part of a team led by Amy Bauer at OOI, Woods Hole Oceanographic Institution. Other team members, are John Bologna at University of Oregon, Carrie Bruce, and Jessica Roberts from Georgia Tech. That's in addition to Amy Bauer and to Leslie. And I think you'll agree it's a pretty exciting new way to hear the ocean. And with that, we'll go ahead and play Leslie's talk. Thank you.
Can you see my screen?
I can see it. Thanks.
Okay, great.
Which is exploring best practices for displaying ocean data with sound instead of with traditional visual displays. The results will help provide better accessibility for all learners to data presented in museums and aquariums. The team is using 5 data nuggets for this pilot project. Data nuggets are small, curated data sets extracted from the vast OOI data archive and pre-packaged for educational purposes. To give you the idea, the following video displays a time series of CO2 flux measured at the OOI endurance array for 1 year. You will hear different sounds for when the ocean is exhaling CO2 versus inhaling, with volume proportional to amplitude. The choice of breath-like sounds is purposeful, intending to help the learner recognize air-sea CO2 flux as something like the ocean breathing. You hear a voice announce the months so the listener can relate the sign and amplitude of the flux to time of year. Listen.
January. February. March. April. May. June. July. August. September. October. November. December.
This project is in its early phase, and the team looks forward to sharing updates over the next 2 years.
Pretty cool.
Yeah, very cool. So, I mean, obviously we don't have Leslie or the rest of the team here. I don't know if there's a way, Darlene, maybe by the end we could drop their contact information in the chat or whatnot, if people are interested in reaching out to Amy or Leslie or any other members of the study team.
I will put their contact information in the chat. Good idea.
Thank you. And with that, our final talk is Karen Bemis of Rutgers, the State University of New York, talking about using acoustic imaging to monitor focused and diffuse hydrothermal venting. Thank you very much, Karen.
Thank you. Here we are. So I just wanted to highlight 2 different deployments of COVIS, which is the Cabled Observatory Vent Imaging Sonar. It's a sonar specifically designed to monitor hydrothermal flow regimes at venting sites. So COVIS was initially deployed for 5 years on the Neptune Observatory by the Ocean Networks Canada. And recently we've been doing some work reanalyzing the data and looking at our reconstructions of the plumes rising above grotto vent. And so what I've observed looking at annual histograms of the plume bending azimuths is a systematic change in bending direction between 2010, when things were more or less north-south, to 2014, when bending is almost entirely northward. And analysis of this suggests that this is most likely to be due to a change in the net background current, and that the net background current is largely controlled by the overall venting on the 5 main vent fields in Endeavour segment. And likely this is due to either increased venting at high rise or decreased venting in the main Endeavour field or Mothra over this 2010 to 2014 time period. COVIS is currently deployed at Ash's Vent Field on the Ocean Observatory Initiative's cabled array, regional cabled array, where we've been focusing more on diffuse flow. And we've been able to use the travel time and decorrelation to map out where diffuse venting is most intense, which tends to be nearest to focus vents, although some of these focus vents are mini smokers that are actually venting clear fluid. And we've estimated a heat flux density of about 200 to 400 kilowatts per square meter for the section of the Ash's Vent Field that we're emitting. So it's really exciting to actually be getting heat flux estimates and starting to be able to see changes over time, although the system is not changing very much at the moment. So thank you for listening. And if you have any questions?
Thank you very much, Karen. And I just wanted to check with you. It looks like your posters, your iPosters, are being presented today, or maybe they've been presented earlier today. I just wanted to see if you wanted to put in a plug for people to come visit the poster.
The e-lightning session was earlier today, but the iPosters are still available and will be for some time if you've registered for the meeting. And I will possibly put up a chat time for either Friday afternoon or possibly sometime next week. And so anyway, you can, the iPosters themselves let you reach out to me, or you can reach out to me directly.
Great. Thanks very much. Okay. Well, thank you. And we'll go ahead and start taking questions. And looks like Darlene, you've already got your hand up there.
Thank you, Karen. Sorry about the background noise. I was just wondering how long COVIS will be on site in case you're there when Axial actually erupts.
Great. So we're currently planning to pull COVIS back up in the summer of 2023. It's been operating pretty good, so we've actually extended the deployment at Ash's for 1 year. So it's originally supposed to come up next summer, but we've extended that to 1 year, so to 2023.
So we hope for an eruption in that period.
Crossing my fingers.
Thank you. John Shorebridge, you have a question.
Hey, Karen, that was a nice talk. You talked about heat flux. Could you tell us a little bit about what the characteristic velocities and temperatures are? And also maybe a little bit about what the composition of the fluid coming up is.
Yeah, so COVIS, of course, is acoustic instrument, so we're not directly measuring temperature. The heat flux density comes from measuring a temperature variance and a characteristic time scale. So that's actually how that's computed. I do know that the high temperature vents, Inferno tend to run around 250 to 300 degrees Celsius. The diffuse flow is, it can be very, very low to, maybe 10 degrees. I think we did a bunch of site institute measurements and got a lot of numbers in the sort of 5 to 10 degree range. The little mini smoker that I talked about runs up about 100, 150 degrees Celsius. So it's quite a range. And the diffuse flow, I'm not an expert on the chemistry and composition, but usually the diffuse flow fluids are basically seawater mixing with the high temperature fluids.
And if you took the heat flux and divided by the temperature, what kind, have you thought about what kind of velocity you're talking about for the plume?
Probably pretty, I mean, for the diffuse flow, it's really going to be quite small. Even for the small smokers, we weren't able to measure any in-situ velocities using a flow meter. And the analysis, the visual analysis hasn't, it's been difficult to localize particles well enough to get really clear numbers, but the diffuse flow is not moving vertically very fast.
Thank you.
I have another question if there's no more. Just between the differences between grotto vent and ashes there. You'd mentioned with the grotto, you have the annual histograms of plume bending, and it looks like ashes is a little bit different, that it's more diffuse. Is that related to the kind of bathymetry in terms of the a linear ridge versus kind of I don't know what you'd call the landscape near ashes there?
I don't know. I mean, I don't know whether it's because it's the difference between a linear ridge and the heat flux just gets more focused with the faulting systems there versus ashes in the caldera, or whether it's just sort of, I mean, I would probably say that ashes does have more diffuse venting, and that may be because of that diffuse venting, that the focus venting is not as hot and as intense. Which is not to say that there isn't diffuse venting near grotto. It's just there is. The focus venting there is much more intense. But I would also say that the current regimes in the two areas are very different. The plume bending analysis in grotto, the plumes pretty much bend either roughly northwest or north-northwest to roughly southwest. They're really going up and down the rift valleys, the currents. Ashes' caldera is much more complicated. The flow comes in and swirls around. And so there's not as much consistency in the directions, but also we just haven't spent as much time analyzing that. Much newer data.
Okay, well, thanks very much. I don't know if there are additional questions in the room. We'll give it another couple of minutes there, and then maybe at the end of it here, we've got most of our speakers here. I know Bill had to leave early, and of course Leslie's talk is pre-recorded, but if we'll just wait for a couple more questions, and if there's no other questions, we'll thank folks again, and also give people the opportunity if they've thought of a question for an earlier talk, perhaps. So, not seeing any additional questions coming in. So thank you, everybody. Thanks first and foremost to our speakers, but thanks to the audience as well. And hope you have a great rest of the meeting. Darlene, I know we've got maybe one more OOI event tomorrow that you want to plug. And again, thank you all.
Tomorrow at 11, scientists are going to use the Data Explorer to show how they're using it to answer specific scientific questions. So do tune in. It's on the website.
And thanks. And that's 11 o'clock Central Time, I believe.
Central Time, yes.
Thank you. All right. Thank you, everybody.
Thanks. Hi, guys.
Thanks for coming.